Welcome back to geometry. We are doing chapter 5, section 2 in this book, Bisectors of a Triangle. Okay, so we learned last time the bisect means to cut in half. So here I have a triangle, and this is a right triangle. We can tell right here. And I have decided to bisect or cut in half this side of it. And I did it in where the line coming out is at a right angle, so it is a perpendicular bisector of that side of the right triangle. If you don't understand that, watch section 5.1. Alright, so now if you do this to each side of a triangle, you see some interesting patterns that emerge on where they're going to meet if we did it to each side. If it's an acute triangle, see, I cut this side in half right here with that dot. These two sides are equal. The line is perpendicular. It's a perpendicular bisector. I cut this side in half. Those two sides are the same. I drew a line that's at a right angle. And I cut this side in half. Those two are the same. And I drew a line that is at a right angle. If you do that, they will all meet in the center of an acute triangle. Remember, that means that all three angles are less than 90 degrees. If you do it with a right triangle, they'll meet on the side. They'll meet on the edge. And if you do it with an obtuse triangle, they'll meet way off here somewhere. And I didn't want to run my obtuse line into my other side ones, so I made a really not allowed too big of a dot there, but we'll just pretend like that's a little dot. But you can see it in your book. Look at the examples, it makes sense. Alright? Now, we have a theorem coming up. You know, this is what we use for our proofs, and it is called the Concurrency of Perpendicular Bisectors Theorem. Now, what I have is a triangle, and for each of these, each side I cut it in half, and then I drew a perpendicular bisector and they met in the middle. Okay? The picture of this is in your book on page 273. Okay? And I'll tell you what that circle is doing here in a second. Okay? If I draw a line, let me see what color I want. Let's do something different. Do I have green? Yes, I do. If I drew a line from this point where they all, notice it's acute, so they all met in the middle. If I draw a line from that point where they meet in the middle to the vertices of the triangle, turns out that these lines all are the same length. And this is the center of this circle that we could put around this. And mine doesn't look like it. You need to go look at the picture in the book, because that isn't really the circle. And I don't want to just draw a big old thing. But if you do it right and really cut it in half, and really do it nice, and it's really a circle. That's not even really a circle, it's an oval. But this will meet where this is the center, and these are radii of a circle around the triangle. Now, fancy math talk, we don't say a circle around a triangle. We say it is circumscribed. The circle is circumscribed around the triangle. And these lines we just made are radii. You don't say radiuses. That would be bad grammar and sound country, especially if you say it with my Georgia accent. Okay, so that's what this is. And so in our thing, from PA is equal to PB, which is equal to PC. That is our concurrency of perpendicular bisectors theorem. Now, another thing we can do is instead of cutting the lines in half, we could cut the angles in half. So here I have a triangle, and I have cut the three angles in half with angle bisectors. Notice these lines are not perpendicular to anything. They're just cutting these angles in half. They will meet in a point in the middle of the triangle called the end center. in-centered. All right? So now, here I've got a triangle that I've done this to. Each of the angles, A, B, and C, have been cut in half. They've been bisected, so each of these angles are the same, and they all met at that point P. And this is going to be another theorem. It's going to be the concurrency of angle bisectors theorem. So they all meet in the middle at P, and if we decided to drop a line that went from P perpendicular down to the side. Oh, I don't want it to be green. That could be confusing. Let's try a new color. Let's make it black. Okay, I'm going to drop a line here that's at right angles. I'm going to drop a line there that is at right angles. I'm going to drop a line there that is at right angles. Okay, everybody see that? If you do that, then these lines end up being equal. And in fact, we could draw a circle here with that line being the radius. That's our radius now, because those are all the same. Now I have a circle inside the triangle. Woo! Before I had a triangle inside the circle. This says that it is an inscribed circle because it's on the inside. This one, inscribed circle. This is a circumscribed circle because it's around the outside. Circumscribed, inscribed. Now, this is the theorem. If you do this, then these lines are all equal. So PD equals PE, which equals PF. All right, so read your book, look at the examples, make sure you understand them, and I don't think it's that hard. It gets a little confusing, you just have to take your time, all right? Math is great, see you next time.